Alrighty, guys. So yesterday we finished up by talking about the concentration of protons and hydroxide ions in solution, right? How the Kw, the equilibrium constant for water, is 1 times 10 to the negative 14. And then if I change the concentration of H plus or OH minus, it's going to have an inverse effect on the other one. You guys remember that part, right? Okay, so now we're going to go into pH, which is the nice way to measure the concentration of H plus. Now, nobody likes looking at scientific notation, right? It gives me a little bit of anxiety too when I see 1 times 10 to the negative 14, negative 10. And so instead of doing that, we like using regular numbers. So we use pH to express the concentration of acids and bases. And so just make sure you guys have this formula down. Okay, pH is the negative log of the concentration of H plus in a solution. Okay. pH is the negative log of the concentration of H plus in a solution. Okay, and so down here, you guys don't need to copy this down, but pH for a neutral solution where you have the same number of acids or H plus and OH minus is negative log of 10 to the negative 7, which is going to be 7. So 7 is water. It's neutral. It's a neutral solution. And here we have this little chart just to show you. The key things that I think you just need to know are that if it's less than 7, it's acidic. If it's greater than 7, it's basic. Okay. And then 7 exactly is neutral. So you know how some girls are very basic? When I go to the mall with my wife and I see a basic girl, I say, hey, that girl's so pH 12. That's exactly how my wife responds. She just looks at me. All right, anyway, let's move on. So I thought it was fun. I think it's funny, dude. I thought I was a genius when I came up with that, but nobody appreciates it in their time. Anyway, whatever. When I die, you guys are gonna remember that at my funeral. And then you can be like, Mr. was so funny. He's a comedic genius. Anyway, so yeah, 7 is when you have a neutral solution. Acidic is anything underneath, and greater is basic. Just remember, make sure you have that formula down. Okay? You guys ready to move on? All righty. Okay, so we got the pH scale. You guys, please don't copy this down. This is just to kind of give you an idea of some of the things in our life that are acidic and basic. So I'm gonna zoom in a little bit. So neutral, we have a pure water. Okay, and as we get more acidic, so milk is a little bit acidic, coffee is a little acidic, and then the further down you go, it gets more and more acidic. Okay, with your stomach acid being pH 1. Okay, and then as you go to the right, it gets a bit basic. So eggs, baking soda, soap, bleach, and then down here are alkalis, okay, which we'll talk about later. But that's just kind of a way to kind of visualize things in our life that are acidic and basic. So one way that we can, so when you guys have heartburn, right? It's when you have a overproduction of stomach acid. A good cure is you can actually take some baking soda and it might help you out a little bit. I mean, an acid would be better, but if you guys really need to, baking soda is a useful solution. Anyone want to explain why baking soda would help relieve heartburn if you have too much stomach acid? Yeah, they're gonna neutralize each other, right? The baking soda is gonna react with the acid in your stomach, and then it'll meet somewhere in the middle. So it'll make the pH closer to neutral. Okay. All right. So let us move on. So I have this problem right here for you guys. I'll do part 1 with you guys, or part A with you guys, and I'll have you guys do part B. Part A is super easy. It's just asking us to calculate the pH. So we know the equation is pH is the negative log of the concentration of H plus. And so here we can just plug in negative log 3.8 times 10 to the negative 4 molarity. Let me grab my calculator real quick. And then let's see if I get the right answer, because I make a lot of mistakes. Okay, so the pH for lemon juice is going to be about 3.42. Everyone got that? Yes. Okay. All right, I'm gonna have you guys do part B. It's the harder one because I need to know how to do this too. So I need you guys to solve this for me. Teach me how to do part B. Okay, you got window cleaning solution, and the hydroxide concentration is 1.9 times 10 to the negative 6 molarity. So I'll give you guys maybe about 30 seconds, or actually I'll give you a minute to do that. 30 seconds too short. All right, guys, 30 more seconds to finish that one up. Alrighty, you guys ready to go? Alrighty. If you're finishing up your last, I guess, little parts of the problem, feel free to do that, but I'm gonna start going through it. Okay, so the key thing you guys wanna see here is that I can't just plug this into the equation, right? And it's because pH is going to be the negative log of H plus. This is the concentration of OH minus. And so what we need to do is we need to use this value to find the concentration of H plus. Now we do have an equation, and the equation is that the equilibrium constant for water is equal to 1 times 10 to the negative 14. And that is equal to the concentration of H plus times the concentration of OH minus. Guys, remember this part from last time? So if I have OH minus and I have 1 times 10 to the negative 14, I can rearrange that equation. And so I can do 1 times 10 to the negative 14 divided by the concentration of OH minus, and that will give you H plus, which you can use to plug into the pH formula. So I'm going to do that right now. So I'm going to replace OH for 1.9 times 10 to the negative 6, and that is going to give me a value of 5.6 times 10 to the negative 6 molarity, and that's going to be for H plus. You guys get that? Or did I mess up? You guys are looking at me like I'm crazy. Okay, I'll double check. Teaching smart kids has made me really insecure. 5.26 times 10 to the negative 9. Dude, I suck. I suck at chemistry. Okay, so that's going to be the concentration of H plus. Okay, and then so all we need to do is plug this into the pH formula. And so we get negative log of that, and that's going to give us an answer of 8.278 for our pH. Oh, I was looking at the wrong problem. I'm stupid. Actually stupid. All right. Yeah.
I did this. The first way I did it was I found the concentration of OH, but since I know it doesn't apply, I think 14.
Yeah.
I just subtracted and got something.
Yeah. So that's fine too. Yeah. We'll get to that in a second. You're basically cheating. Cheaters. Cheaters. I'm just kidding. All righty. So we're gonna move on to another question. Now this one is gonna require you to think a little outside the box. Some of you guys might know the answer already, but the important thing is the explanation. Okay. So I want you guys to look at 12.15. Is it possible for a solution to have a negative pH? Okay. And if so, would that signify an acidic or basic or acidic solution? But I want you guys, more importantly, to explain why. Why can we have or cannot have a negative pH? So I'll give you guys a minute. You can talk it out with the person next to you. You guys don't have to write anything down if you don't want to, but just talk it out. See if you can figure out why we can have or cannot have a negative pH. Take a second to talk it out. Alrighty, guys. You guys talked that out? Okay. So some of you guys might already know the answer if you guys watched the videos and whatnot on this before, but it is indeed possible to have a negative pH. So the answer is yes, you can have a negative pH. Okay. And so if I have a negative pH, would that be acidic or basic? Yeah, acidic, because the pH, if it's negative, it's going to be less than 7, which means that it's going to be acidic. Now let's talk about why. Okay, so if you look at the pH formula, negative log of the concentration of H plus. Okay, your understanding of this is going to depend on how well you understand logarithms. But if you rearrange this equation to solve for H plus, let's say I wanted to find H plus, how would I isolate H plus? Yeah, you would have to use an exponent. So the first thing you would want to do is you want to move the negative to this side. So negative, the negative of the pH. And then you would put everything to the power of 10. Okay, that's how you can get rid of a logarithm. And the 10 and the log will cancel out. And on the right side, you'll have the concentration of H plus, and you'll have 10 to the power of negative whatever the pH was. Make sense so far? Okay. So you guys can check this in your calculator, but basically, if you have a pH or if you have a solution where the concentration of H plus is 1, can somebody punch that into their calculator and tell me what they get? 0, yes. Okay, which makes sense because 10 to the power of what is going to give you 1? 0, right? If the concentration of H plus is 1, you would need 10 to the power of 0 to get it to 1, right? Now, you guys can punch this into a calculator for me now. If I have a solution where the concentration of H plus is 1.1, what is the pH? Calculator. Yeah, negative 0.04, right? Okay, so you see that since we have a logarithm, we can get a negative pH, right? So basically the point is, if you have a solution, so if the solution has a concentration of H plus that is greater than 1, the pH is going to be negative. Okay, so if you have a solution where the H plus concentration is greater than 1, the pH is going to be negative. Okay, and these are for super duper acidic compounds. Okay. And since you guys are probably wondering now, what is the lowest pH that we can get to? The lowest pH substance that we can find is, let me pull it up. It's a compound called fluoroantimoic acid, and it has a pH of negative 31.3. And so it might be kind of hard to understand what that means, but let's just think about it this way, okay? When you have a logarithm, okay, when you change a whole number, it changes by a factor of what? It changes by a factor of 10, okay? So 7 is pure water, right? Okay, so when we go to a pH of 6, that means it's going to be 10 times more acidic. And then if we go to 5, it's going to be another 10, but what's the difference from 7 to 5? It's going to be 100. And then if we go to 4, what's going to be the change from 7 to 4? Yeah, so it's not going to be a 1-to-1 ratio. Every time you change a whole number, it's going to change by a factor of 10. So here we're going down until we get to a factor of 31.3 times greater than that. So that's going to be what? 1, 2, 3. That's 3 zeros. So this compound is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and a little bit of change times more acidic than water. And if you wanted to compare that to stomach acid, which is pH 1, you would just have to get rid of 7 of these. So it's this times more acidic than your stomach acid. And so you can see that is very, very acidic. I think battery acid is 0, so that times more acidic than battery acid. Okay, so super duper acidic. Just a fun fact for you guys. But that's basically how logarithms work. All right, any questions about logs? pH, we're gonna be looking at this a lot, yeah. Oh, they make it. Yeah, people are weird. It's like, how can we make a compound that's more acidic than anything else? Yeah, definitely not found in nature anywhere. Good question. Yeah. Hey, I mean, we have a thing. Well, it says it'll eat through skin, bones, and pretty much any other container.
Oh.
Yeah. Yeah. They can't.
Oh.
Yeah. Yeah, I know there's a compound that's super explosive. It'll explode without doing anything. Like if you fart in the general direction of that compound, it'll just blow up. You guys can look it up. I think if you look it up on SciShow, like either this or like most deadly chemicals, they have a fun video. I love this channel. Anyway, shameless or plug for them, I guess. Okay, so we're gonna look at some other P scales. So we have pH, which is the negative log of the concentration of H plus, right? We also have something called POH, which is actually the one that I prefer. Can you guys guess why? It's me, Paul O. Okay, so that's the one I like. But POH is the negative log of the hydroxide concentration. Okay, unfortunately, everybody tends to like pH more, so we'll use pH more. But if I had I'd force you guys all to use POH only. Okay, and it's the opposite of the pH scale. So on the pH scale, as the numbers get smaller, it gets more acidic, right? And then on the POH scale, the smaller the number gets, the more basic it gets. So it's basically the opposite of pH. Okay. And so here's a bunch of math that you guys can look at to prove how this system works. But one of the important things that Josh mentioned earlier is this right here. And this will be very helpful as you guys do your math. pH plus POH will always equal 14. Okay, even if the numbers are negative. All right, with that being said, I'll give you guys a minute to try number 16. Okay, what's the pH of a solution that has a POH of 3? This one should be really easy. And is it acidic or basic? Yes. All right, this one should have been pretty easy, guys. So all we need to do is plug and chug into this equation. So if POH is 3, and then we know that sum is 14, what's going to be pH? Yeah, 11. Super easy. Okay, and this is going to be basic. Okay, there's two ways you can look at it. You can look at the pH, it's greater than 7, right? So it's going to be basic. And then the POH is less than 7 because 3, so it's going to be basic. Easy peasy. All right, let's do one that's a little bit more challenging. I want you guys to try 12.17. And then if you guys think you can, I'm going to make another copy of this just so it's easier for you guys to see. But I want you guys, if you think you can do this one, to do 12.18 as well. Yeah. Give you guys a minute to try that out. Do you need the equations?
Wait, no.
Actually, I'm going to write them anyway. So I'll write them now for you, Josh. Because I know you like to cheat and look it up. Just kidding. Misclick. Lag. Dude, the things that gamers say when they mess up. Oh, my bad, lag. Hi, ping. All right, maybe 30 more seconds to finish up. Okay, at least try to get 17. If you can get 18 as well, then that's good too. Are you going to be rolling for Raiden? C2? I heard the damage increase is crazy. I don't have her. I'm probably rolling this time. That's the biggest regret of my career. Janelle, do you have Raiden? Are you going to be pulling for her? No. Are you saving? Sorry, what was that? Oh, you stopped playing. Okay. It's good. Get out while you can. Alrighty, guys, let's go over this one. Okay, so 17, super simple. We have a pOH of 10.24. Okay, so we have a pOH for 17, which is equal to 10.24. Now, we know that pOH is equal to the negative log of the concentration of hydroxide. And so if I'm looking for H plus, there's two ways that you can do this. The first thing you can do is you can convert this into pH. I think that's the easier way to do it. So you can do 14 minus 10.24, and that will give you a pH of 3.76. And that's equal to the negative log of H plus. From there, what you can do is put everything to the, move the negative sign first, and then put everything to the power of 10. That'll cancel out. And then so the concentration of H plus is going to be equal to 10 to the power of negative 3.76. Okay. And then you can just finish that up and you should get 1.738 times 10 to the negative 4. And that will be your answer in scientific notation. And then molarity. Okay, the other method that you could have done is you could have used this to find the concentration of OH minus. And then we know that it's going to be the equilibrium constant of water divided by H plus. And then we can calculate out for H plus like that. Either way works. You'll get the same answer. Any questions on that one? Yeah, the math gets more confusing now because we're going to start using logs a lot. And don't worry, guys, we have ice tables coming back, quadratics coming back, and then we got logs too. Okay, and then 18, I'm going to do really quickly. Same thing with 18. The pH is 9.18. That tells us that the pOH is 4.82, and then that's equal to the negative log of OH minus. And then you can do all the calculations out for that. But I got 1.5 times 10 to the negative 5 molarity. And that's what you should get for 18. Okay, so just make sure you guys get really comfortable working with the logarithms, because once we go forward into the ice table problems, instead of giving you concentration sometimes, it's just going to give you the pH or POH, and then you got to convert it into molarity and then plug it into an ice table and then solve for equilibrium like that. So a lot of different steps in the problems. Elaine's already sick of it. I told you guys to ditch this class, but then y'all are like, nah, I can do it. And you guys can't, but is it worth it? At what cost? Everything. Okay, let's move on. You guys ready to go? Yeah, sorry if I'm going really fast, but I said pedal to the metal. Make sure you guys read these textbook pages, which I know you guys always do, about how to measure pH. There's different methods, and we'll be doing them in labs, and so you'll just need to know how to do that. Okay, strong acids and bases. We've talked about this before, but there are 7 common strong acids. Basically, strong acids and bases are strong electrolytes. Strong electrolytes are compounds that almost completely dissolve in water. Okay, so that's why they're called strong. They just break apart. Okay, and there's 7 strong acids that are common. You'll have to know these, just to let you know. HCl, HBr, HI, HNO3, HClO3, HClO4, H2SO4, and HNO3. Why did I put the and there? English. Okay, there we go. So basically, this is the reaction that you'll see. If you put them in water, they dissociate completely. That's what a strong electrolyte is. It dissolves completely. And a weak acid would be something that doesn't completely dissolve. Okay. And a key thing that you want to notice is that we didn't use equilibrium arrows because it's not an equilibrium. It doesn't go in the reverse reaction. It goes only forward. It only goes to the right. Make sense? And don't be stressed about writing down the names of the common acids. It's on, like, you can do a quick Google search and then it'll come out. Yeah. Huh? That's why the and was there. Thank you. Like I said, guys, I'm not the smartest person in the world. I appreciate it. I know. The world will see, because everyone watches these videos, how dumb I am. I'm okay with that. Does it?
Sure.
It doesn't get any views. Nobody watches these. Okay, so basically what this tells us that in a strong acid, the acid is the only significant source of H+ ions. And so it's very straightforward to figure out the pH of these solutions because everything dissociates. Okay, it gets a little more complex later, but I'll show you guys what that means in a sec. So, hey, what's that? Huh? Yeah, go ahead. Okay, so let's take a look at the pH for this compound right here. Okay, so HClO4, is this a strong or a weak acid? Strong, yeah, this was on our list, right? So this is a strong acid. Okay, what that means is if we have HClO4, it's going to break down completely into H+ and ClO4 minus. You can leave it like right there. I'll keep it out. I'll see it. Okay. So this tells us that HClO4 has a concentration of 0.04 molarity, right? So if it breaks down completely into these 2 compounds, what is the concentration of H+ when it breaks down? Not 1. This guy is 0.04. It's going to break down completely. Yeah, 0.04. Thank you. 0.04 molarity. And then what's the concentration of this guy? Yeah, 0.04 because it breaks down completely, right? We had H, we had ClO4, and it's going to break down into H and ClO4. It's going to have the same concentration. So that's the point that I'm trying to make. In a strong acid, the H plus concentration is going to be equal to the concentration of the original acid. Okay, so let's try this again. If we had a strong acid that has a concentration of 0.1 molarity, what's the concentration of H plus? 0.1, thank you. What if it was 10 molarity? What's the concentration of H plus? 10, good. Okay, so that's the point that I'm trying to make. Okay, from there, super easy to find pH, right? We just need to do pH equals the negative log of H plus. We can see that the concentration of H plus here is going to be 0.04. And then we just plug that into our calculator and we'll get a pH of 1.398. And this makes sense because if we have a strong acid, we're going to expect the pH to be low, right? Because it's very acidic. And so we indeed do have a very low pH. Okay, I want you guys to try 12.20 on your own. Okay, 12.20, if you can't see it very well, you are looking at a solution of HNO3. It has a pH of 2.34. What is the concentration of the acid? Okay, this one might be a little bit trickier, but I'll give you guys a minute to try it out. Feel free to work with the person next to you. She's so strong, it's not even funny.
I think that's important.
Who'd you say is first? There's only one right answer. No, it's not.
Yeah.
It's Benny Boy.
Okay, no,
Bennett is the Pyro Archon. I don't care what nobody says.
not true.
It's true. He's the best.
Healing is the attack.
Raiden, I think, is the best offensive support just because the energy recharge. Zhongli is probably the best defensive because the shield, like you can smash your face on the keyboard and beat everything. And I'd say Xing Chu is the other one. That's number 4. He's crazy too. Okay, ready to go, guys? All right. So, is this a strong or weak acid? HNO3.
Strong.
Strong, very strong. So I'm gonna draw some biceps. All right, very strong. Like that. This is a strong acid. Yes, strong acid. Okay, pH of 2.34. Okay, so we know that pH is equal to the negative log of the concentration of H plus. Now, we know that if we have a strong acid, right, that it breaks down completely into H plus. And so what that means is that their concentrations are going to be equal to one another. So if I can find the concentration of H plus, I can find the concentration of the strong acid. So what we're gonna do is just plug these numbers in. We got 2.34. I'm gonna move the negative to this side, is equal to the log of the concentration of H plus. How can I isolate the H plus? Yeah, power of 10. Okay, 10 to the power. That's going to cancel that out. We'll get H plus on the right side. And on the left side, we'll get 10 to the power of negative 2.34. And that's going to give me an answer of 0.00457 molarity. And since it's a strong acid, this is going to be the concentration of HNO3 as well. They're going to have the same concentration. Okay. Make sense? Just trying to get you guys as much logarithm practice as possible. All right, so that's strong acids. We'll get into weak acids in just a second, but we're gonna go into strong bases now. Okay, so strong bases are same thing, strong electrolytes, but instead they're going to be the ionic hydroxide of the alkali metals. Okay, if you guys remember on your periodic table, do you guys remember which column are the alkali metals? Yeah, the first one. Okay, so Na, NaOH, KOH, and other ones like SrOH2, these are strong bases. And there's a list online you can probably find. Strong bases are a little bit trickier. We talked about this back in Unit 4, so I'm not going to spend time talking about it. But it's not going to be just groups 1 and 2. So just make sure you keep an eye out for that. Okay, so same thing here. If you have a strong base, so it's going to break down completely into the ion that compose it. Okay, so it's going to break down completely. So the concentration of OH minus is going to be equal to the concentration of the strong base. Okay, same thing as before. All right, so this one's a little bit of a creative thinking one. I think a little outside the box, but I want you guys to try 12.21. Okay, you got two strong bases, okay? They're both strong bases. This is a strong base, and this one is also a strong base. I want you guys to tell me which one is more basic. 0.001 molarity solution of NaOH or a 0.001 molarity solution of BaOH. Okay, so take a minute. You can work with the person next to you, and then after that, we'll go over it together. All right, hopefully you're able to think about it. You guys ready to go over it or still working? I just see the tops of your head, so I'll give you guys another 30 seconds. You clear Abyss though, Josh?
No.
Do you 36 star it or?
God, no.
No, okay.
The best I've done is like 34.
That's good. That's usually where the wall is. Yeah, 36 it was a tough wall for me too. I had to build Ayaka in order to get the 36.
Oh,
She's insane. You have Ayaka?
Yeah.
She's actually busted. I'll show you my Ayaka during the break. I started streaming, so I have recordings of everything, and I did the Abyss yesterday.
I thought you know, there's that new area. Well, I would think like
Enkonomiya, the bottom one. Yeah.
There's those like answer night looking dudes.
Oh, in the event.
Yeah.
Yeah. No, that event was so fun. I just love exploring.
Right.
Alrighty, guys. So let's go over this. Now, here we have the same concentration, and so what we really need to look at are their equations. So we got NaOH, which is going to break down into Na plus and OH minus. Okay, so if I have 0.001 molarity NaOH, what is the concentration of my hydroxide? Yeah, 0.001 molarity. Good. Okay, now if we look at barium hydroxide, though, how many OHs do I have? 2. So if this breaks down I need to make sure that I remember that it breaks down into 2 OH minuses. So if the concentration of barium hydroxide is 0.001 molarity, what's the concentration of the hydroxide? Yeah, 0.002. It's going to be doubled because it breaks down to 2 hydroxides. So back to the original question, which one is more basic then? Yeah, this guy is going to be more basic. And if you want to do the calculations, you can, because the pH or pOH of this solution, the first solution is going to be, 3. And then the, oh, I don't even need, why am I doing the math for this? And then the pOH for this guy right here is going to be 2.7. Okay, so this one is going to be more basic. All right, makes sense? It just releases more hydroxides, which is automatically going to make it more basic. All right, we'll just do one more section and then we will move on. God bless you. Okay, we are going to skip 12.22. And then we're going to go jump straight into weak acids. Now, weak acids, and I want you guys to make sure you're very aware of this. They only partially ionize in water, okay? So only some of the weak acid molecules are actually going to break down. So I got a little diagram for you here. Strong acids, everything breaks down into the ions. But in a weak acid, it's going to be an equilibrium. Only some of the molecules break down, okay? So here you go. Okay, so if this is the weak acid right here, oops. Okay, if HA is our generic weak acid, some of it's going to break down into H+, some of it is going to break down into the anion. Okay. And the amount that it breaks down is going to depend on the equilibrium constant. The equilibrium constant for an acid, instead of Kc, we use Ka. Okay, and Ka is going to be corresponding to this right here. Okay, same thing as usual. Concentration of products divided by the concentration of the reactants. Okay. You guys ready to try a problem? All right. And then we'll do this one and I'll have you guys go on your break. Okay. We got a big chart right here, 4 different compounds. I want you guys to figure out the strongest weak acid. Okay, so weak acids have different amounts of strength. Okay, if it's strong, so the stronger an acid, the more it breaks down. Okay, so I want you guys to take a look at this table and I want you to figure out basically which one of these acids break down the most in solution. I want you guys to write a quick sentence describing why. Why does your choice break down more than the others? Take about a minute to do that. Alrighty, guys. So I want you guys to show me with your fingers. Which one do you think is going to break down the most? 1, 2, 3, or 4? Fingers, fingers, gang signs. Okay, so let's take a look at this. So hopefully you guys were able to identify the thing that you need to look at is Ka. Okay. Okay, now Ka is equal to the concentration of the products divided by the concentration of the reactants, right? And so every single one of these acids is going to break down in to some extent to H plus and the N acid, the conjugate base. Okay, so if we take a look at this, if it breaks down more, are we going to have more reactant or less reactant? Okay, so for a stronger acid, is it going to be a bigger numerator or a bigger denominator? Yeah, the stronger it is, the more it goes to the right, right? So the more it goes to the right, what happens to the numbers for here? Bigger. And where do these numbers go? They go on the numerator. Yeah, it gets confusing, right? These guys go on the top. These are the numerator. Okay, so if the numbers on the top get bigger, does the Ka get bigger or smaller? Bigger. So which one of these Kas has the biggest number? Yeah, so chlorous acid breaks down the most. It is the strongest out of these weak acids. Okay. Okay, so this guy is like the high schooler playing basketball with a bunch of elementary kids. He's the strongest, but still weak. Okay. So that's how you can tell. The bigger the Ka number, the stronger the acid. Alrighty, guys, that was a lot of stuff. We went really fast through this, so I'm gonna give you guys a quick 5-minute break. Go to the restroom, do what you gotta do, and then we'll come back and we'll finish up for today. Okay, so I'm gonna briefly go over how to calculate Ka from pH. And so we talked about earlier how Ka is equal to the concentration of H plus and the conjugate base divided by the concentration of the acid, right? This is just a Ka formula. Now we can take pH because when we measure in labs the strength of an acid, we usually find it in pH. We don't find it in the concentration of H plus. And so it's useful to be able to go from pH in order or to find Ka. Okay, because Ka is what we use for equilibrium, like ice tables, but pH is more practical application in labs and things like that. Okay, so we'll do a sample problem to showcase that, and I'll have you guys do a couple on your own. But here we have a 0.1 molarity solution of formic acid, and the pH is 2.38. Okay, so the pH is 2.38. Okay, now I do want to point out that formic acid is a weak acid. It does not dissociate completely. And then we're trying to find the Ka for formic acid. Now, if you think you could try this on your own, feel free and go ahead, but I'm going to take it step by step. Okay, so if we have the pH, what we can find naturally is the concentration of H plus. Okay, and the reason why we can find H plus is because of the formula, the pH formula, negative log of H plus. So what we can do is rearrange the equation so that we have negative 2.38 is equal to the log of H plus. Okay, so same thing we've been doing. We put everything to the power of 10, the log will cancel out, and then H plus will equal to 10 to the power of negative 2.38. Any questions on how we got to that step? It's pretty much what we've been doing until now. Okay, and then from this, you should get an answer of 4.2 times 10 to the negative 3 molarity. Okay, so the concentration of H plus is 4.2 times 10 to the negative 3. Okay. So far, so good? Okay, now what we have to do is we need to write the equation for formic acid. So this is formic acid, and we're going to write the chemical equation. So it goes into equilibrium and it breaks down into H plus and the conjugate base, COOH minus. Basically, it just loses an H. What's up?
Are you telling me this is supposed to be 11 instead of 12?
This isn't rates, right? Was this rates? I think that's rates.
That's the first.
No,
unit
that's
of
12. That's
equilibrium.
12. That's 12.
So you have two 12s.
Wait.
You numbered them.
Dude, I do not. I'm sorry. I don't know it now.
You do. Saying
Oh,
that. So
By
you-
the way, I'm being recorded right now. Oh, wait,
Oh,
we
sorry.
are on 12. No, you're good. No,
But
yeah.
even that it's number 11, that's
Yeah.
12.
This should be 11. No, you're good.
That
I
should
was
be
wrong.
11.
This is 11. Yeah.
I don't care. I can adjust it.
Oh,
So
just
then I
wanted-
just started, my numbering started going off. I'm like, oh my God, I messed up again.
Yeah, no, it's me.
I didn't mean to interrupt you.
No, you chilling. I just want to let you know that your beautiful voice is being recorded. And you
Oh.
know, California is a consent state, so.
Trust me.
Oh
They're
no,
gonna want to cancel that video for the last 45 seconds.
nah, it's for you. Okay, so we got our reaction of how it breaks down. And what we need to do now is everybody's favorite ice table. And the reason why we need to make an ice table is because what do we have? We have the initial concentration of formic acid, which was 0.1 molarity. How much of these do we start with? 0. Yeah, we didn't start with any. Okay. We know that we're going to lose some formic acid to form H plus and the conjugate base. We just found out that the concentration of the H plus is going to be 4.2 times 10 to the negative 3, which means that COOH is also going to be 4.2 times 10 to the negative 3. That's going to be your change. And so the equilibrium concentration of formic acid is going to be 0.1 minus 4.2 times 10 to the negative 3. Okay, now I know I went through that pretty quick, but does that make sense? Hopefully. Okay. Now, since we're trying to find Ka, all we got to do is plug this into the formula for Ka, and then we're all done. Okay, so let's plug it in. I'm going to do it up here just to have a little bit more space. But the Ka is going to be equal 4.2 times 10 to the negative 3, but I'm going to square it since I got it 2 times. You square that. And then my denominator is going to be 0.0958, just because I subtracted those two values. And so if you divide that out, you should get a Ka of 1.548 times 10 to the negative, what is that? 5. But let me double check my math real quick. Oh, 4. My fault. Wait, that's not what I got at all. 1.84 times 10 to the negative 4. Right? Oh, Mr. O, you're so dumb. 0.0948. Yeah, that should be this should be correct. Yeah, 1.84 times 10 to the negative 4. Okay. And that's going to be your Ka. So that's how you want to solve for Ka. All you got to do is just plug in your values. That's what I wrote down. What am I looking at? All right, you guys ready to try one on your own? Okay, we'll try one on our, I'll have you guys try one on your own. And then after that, we'll be done for the day. Okay, so let's move on to 12.25. Anybody need to look at this still? Chilling? Okay. We'll go 12.25. So 12.25, it says the 0.02 molarity solution of niacin has a pH of 3.26. What is the acid dissociation constant for niacin? Now, I didn't give you the formula, but niacin is a weak acid. That's all I'll tell you. Okay. Niacin is a weak acid. So I'll give you guys about 2 minutes. Find out the acid dissociation constant, another way of saying Ka. Okay, so I have the formula for pH set up for you guys already. Again, same thing we've been doing literally all day. Just want to move over the negative, put it to the power of 10 so you can get rid of the log, and you should get a concentration of about 5.5 times 10 to the negative 4 molarity for H+. Okay, now you didn't have the formula for niacin, but if you guys remember, acids kind of have a generic formula where we can have HA, and then we can set it up equilibrium. I told you it's a weak acid, and it's going to be H+ and A-. So even if you don't have the formula, you can still kind of figure out what to write down. You could have done HA, HX, You can even write niacin, and then here you could write niacin minus H. You can kind of just write down whatever you need to get that information. Okay, we're going to set up an ice table. And then we're going to plug in our values. So we know that it's 0.02 for niacin initially, so 0.02 molarity. We know that we start with 0 for both of these. We're going to lose some of the acid and gain H plus and the conjugate base. We can plug in our values right here, which means that our value for HA is going to go from 0.02 to 0.02 minus 5.495 times 10 to the negative 4. Okay. And after that, we just plug it into our Ka formula. So on the top, we'll have 5.495 times 10 to the negative 4, and I'm going to square that. And then we're going to divide that by 0.02 minus 5.495 times 10 to the negative 4. Okay. And then after that, we should get a final answer of 1.548 times 10 to the negative 5. I guess this is where I got that earlier. All right, and that's it. That's how you can find the Ka value using just the pH and the initial concentration of the acid. So hopefully not too bad. All right, just a reminder before we finish up that make sure you guys stay on top of your homework. Some of your homework might be more past what we learned in class. So just make sure you're keeping up with the textbook reading. And if you have any questions, make sure you guys let me know, okay? But good job today, everybody.